Welcome to Brain Vision.
So here we're going to solve problem 3831. The question asks us to plot frequency versus stopping potential. So in order to do that, we're going to use an equation. But first, let's write down the steps. We're going to convert our wavelengths. Wavelengths, I'll put omega as the symbol for wavelengths, to our frequencies, which is f. And we're going to use an equation that's given to us. It's assumed that we can use this and that we know this. C is equal to omega f. I'm sure you know this equation, where c is the speed of light, which is 3 times 10 to the 8 meters per second. To get our frequencies, we just rearrange like so. F equals to c over omega. Now, it just so happens that our frequencies are going to be in the magnitude of the hundreds of trillions, which is around the 10 to the 12, 10 to the 14 range. So what I'll do is I'll write the frequencies in times 10 to the 12. So whatever number I write down, I'll just multiply this. You should assume that it's multiplied by 10 to the 12. Okay? So in other words, it's going to be in terahertz. So our frequencies that we get from using the equation from below are in terahertz: 820, 740, 688, 610, 550, and 518. So now that we've gotten that done, our second step is to graph our frequency in the x-axis I'm going to graph our frequencies on the x-axis and our stopping potential on the y-axis. Okay, so let's draw our graph here. These are our axes. Our frequency is going to be on the x-axis, our stopping potential on the y. And our data does not start at 0, so I'll kind of write this mark here to indicate that. Our frequencies start around 500. By the way, this is whatever number it's going to be multiplied by 10 to the 12 hertz, just like how I wrote above. So it's around 500 terahertz all the way up to over 800 terahertz. So we'll just do this for good measure. The stopping potential goes all the way up to about 1.5 volts. So and anything above 1.4 we'll just plot above there. Okay, so let's plot our data, and I'll plot it and I'll speak afterward so that we can go by fast. But for the first one, actually, I'll just say we have 518 terahertz corresponding to 0.24 volts for our stopping potential. It's about there. Next is 550 and 0.36. Okay, we have 610 and 0.62. And I'll just go ahead and plot the rest. Right. Okay, so now that we have our data plotted, I want you to notice that it's it's sort of positively correlated and it's linear. So we're going to use point slope form, which is our formula for lines, and we're going to use that with another equation that's given to us and solve some of the questions. So our third step here is to use an equation that's given to us, and that equation is 38, equation 38.4. That is given in, of course, chapter 38, and we're going to use that with point slope formula. Sorry, guys. Point slope formula. And we all know what a point slope formula is. It's y equals to mx plus b. And equation 38.4, which is given to us, is equal to this. It's EV, or EVO, which is the stopping potential, equal to the energy of light, which is Planck's constant, times the frequency of light, minus the work function of the material. Now, we're going to have to rearrange this to make this look like point slope form. And to do that, we just divide by E on both sides, which is the charge of an electron, by the way. E cancels on that side, and you're left with VO equal to H over H over E times F minus the work function over E. Okay, so you can see that we have our stopping potential, which is Y, our F, our frequency, which is X, and we have our slope, which we now know. Our slope, which is M, is equal to H over E, and our intercept, our y-intercept, is the work function over, or minus the work function over E. Now, in order to get the slope, all you have to do is pick 2 points on this graph here and use that equation that you learned back in algebra, which is the difference in y between 2 points is divided by the difference in x in 2 points. I won't do that here, but you should know that the value we get for slope is 4.112 times 10 to the negative 15 volts over hertz. It's such a small number because our hertz value is so big. And that's on the bottom. Now for B, all you have to do is use point slope form. Since you know what M is, you can pick any point on the graph, which gives you a Y and an X value, you can get B. So B is negative 1.894 volts. Okay. So these are the two values that we can use to solve our problem. The first problem is to solve for the threshold frequency. Now, with our equation here, the threshold frequency is, I'll write it again. I'll write the equation again. EVO equals to H, or Planck's constant, times the frequency minus the work function. The value of the threshold frequency is when the light has an energy that's exactly equal to the work function. That means the electron on the metal plate of the photoelectric experiment just ejects. It doesn't have any remaining energy. This is the energy of the electron. So in other words, we're saying that this side is equal to 0. But if we divide 0, which is going to be this value here, if we divide it by E and we get this equation, this is going to be 0. VO is going to be equal to 0. So this is what I'm saying here. We're going to say that 0 is equal to H over E times frequency minus the work function over E. If you multiply both sides by E, you would get you'd get 0 equals to HF minus the work function, which is the threshold. That's the threshold frequency, or the point at which you get the threshold frequency. So here, I'll just erase that. Our question, which asks us about the threshold frequency, can be solved easily by just writing like so. F is equal to the work function over E divided by H over E. And we know what these values are from up here. The negative of the work function over E is B. So we're going to get negative B here divided by the slope. And negative B over the slope is equal to 1.894 volts over 4.112 times 10 to the negative 15 volts per hertz. And this value is 4.59 times 10 to the negative 14 hertz. Oh, I'm sorry. It's positive 14, because remember, our hertz is going to be in the hundreds of trillions. It's a very large number. So our threshold frequency is 4.59 times 10 to the 14 hertz. I'll just erase that so it's clear. Our next question is the threshold wavelength, and we can solve that by using the equation that we used above in step 1, which was C equals to omega F. I'm not going to write that again. I'll just write it like this. Our threshold frequency, and here I'll label this thresh, just to make it clear that we're doing the threshold. It's just C over the threshold frequency. And that value, I won't write it all out, is 653 nanometers. That is the answer for this question. So next, we're supposed to solve for the work function in terms of EVs. So we know the work function minus the work function over E is equal to B, and B is equal to negative 1.894 volts. So simply, all we have to do is multiply both sides by -1. That cancels the negative. And multiply both sides by E. And that cancels the E on the left side. And we're left with the work function equals to 1.89 EVs. So that one was the simplest one so far. And the last question is find the value of Planck's constant given the value of E. So our slope, which is m, is equal to h over E. So our h value is equal to m times E. We know what our slope is. And we know what E is. E is the charge of an electron. So if we write everything all out, we get 4.112 times 10 to the negative 15 volts over hertz times 1.602 times 10 to the negative 19 coulombs. And we get an approximate value for Planck's constant, which is 6.59 times 10 to the negative 34 joule seconds. Joule seconds because coulombs can be rearranged to get to be when multiplied by volts over hertz to get these units here. So this value is kind of close to the true value, but this is the approximate value that you get when using this equation. So thank you for watching this video, and I hope it helped. I'll see you